Um, Hello, hi everyone. Welcome to Temporal Graph Reading Group this week. Um, we are very glad to host Zifeng Ding from University of Cambridge, who will be presenting the recent work Self-Exploring Language Models for Explainable Link Forecasting on Temporal Graphs via Reinforcement Learning. And for quick intro for Zifeng, so Zifeng Ding is a research associate or postdoc researcher in University of Cambridge NILP group at Cambridge, and his current research interests include but are not limited to agentic AI, LLM reasoning, in particular temporal reasoning with LLM, synthetic data generation, and LLM hallucination detection and mitigation. So I will hand the mic to you, Zifeng.
Okay. Yeah, I will share my slides. I hope I hope it's fine, right? Everyone can see.
Yeah, yeah,
Yeah,
see you
okay.
well.
So I'm going to tell everyone about our recent work. It's called Self-Exploring Language Models for Explainable Link Forecasting and Temporal Graphs via Reinforcement Learning. Um, so first, let me give you a short introduction. Um, this figure I have reused for several times. So in temporal graphs, we can also call them dynamic graph. Basically, they are the same. So there are two types of temporal graphs, but here I borrow the definition from a very good paper from last year. So they define the dynamic graph into two types. First is the discrete, second is the continuous time. So if we're doing temporal graphs, we know that there are two types of them. One is DTDG and one is CTDG. And from my personal taste, I think CTDG is more how to say refined because it helps us to understand the world like in a continuous way, and it will preserve more temporal details. So people are shifting their focus from DTDGs to CTDGs, like more generally in recent years. And then we all know that reasoning on temporal graphs is actually quite sophisticated because based on the static graph, now we also have the timestamp to model. And a very core problem in temporal graph reasoning is forecasting, is like how we can predict the future graphical data based on the histories. And we think that actually explaining the forecast is also very essential for evaluating the model's quality and assessing its trustworthiness. So for me, I just put here, like I have seen a lot of works that tries to propose new models from different perspectives to enhance the results on the benchmarks. Also, Andy have proposed several benchmarks from real world. It is very nice work. But a lot of people that doing this kind of work, they neglect one problem is that how can we achieve the explainable temporal graph forecasting, which is also very important. So next is that there is also some related work in recent years about the graph foundation model. So when I was trying to do this work, the first motivation is that can we use a language model to achieve a graph foundation model? It sounds very intriguing, but when I start to do this work, I found that it is actually hard, and I will talk about it later. So people start to wonder, okay, can we train a model to reason any graph? It doesn't have to be using language model. It can be using other neural structures or maybe only symbolic structures. So the graph foundation model definition is that we train a model that can be directly applied to different graphs without retraining. And during my PhD, I was doing a lot of inductive representation learning on temporal knowledge graph. But from the comparison, I feel that it is not exactly what means inductive reasoning. And some preliminary works about temporal graph foundation model, they are based on the temporal graph neural networks. Here in this slide, I just show some real, real conversation with me and Xingyue in Andy's group when we were talking about it. And he's an expert of graph foundation model. He thinks that we should do this kind of stuff from generalizing from the GNNs. but I do language models more now, so I think that I don't actually have to do that from that perspective. I can just try to use the language model to do that, because language models, they are called foundation models in text or text image or text video image, audio, graph, anything, because they can transform everything into text generation. If we can unify every task into text generation, it means that we can somehow do a work like a foundation model. And here's a little bit more background about the foundation model that is developed with LLMs. There is some very preliminary attempts. First is the LM for Daiji, which is accepted, I think, last year, maybe in Sigir, I don't remember. They proposed a synthetic graph reasoning task suite to test LM's capabilities, but they did not try to fine-tune LLM. They just tried to see what is the potential of LM to do graph reasoning. And another one is the relational LLM, real LLM. I think it has also been introduced several weeks before in this reading group. They try to encode the graph with GNN and use soft prompt to jointly train with LLM, which is how most people do when they are trying to combine graphical structures with the language models right now. But we found several limitations. First is that LM4 Daiji, they do not touch the real-world large-scale TGs. They use some synthetic graphs, which are, I think, only up to 13 nodes per graph, or 20 nodes, or 30 nodes. I don't remember. It is very tiny. And RealLM is for relational database. Relational database, actually, it is much, much smaller than the real world temporal graphs like Wiki or like Twitter, something like that. So and also it does not force the LM to generate explanation. And what we want to do in this work from our motivation is that we want to use LM to reason over any large-scale real-world temporal graphs without retraining, just like how graph foundation models should do. And we want to use LM to generate human-readable explanations. And here is some very important point here, why we want to do that. If we do a lot of forecasting tasks, if you're familiar with that, we know that real-world forecasting, we don't have ground truth labels before the actual event happens. This is quite tricky, and the labels in the temporal graph forecasting datasets does not mean anything here, because in the real world, we don't even have these labels, and we need the explanations to indirectly evaluate the quality of our forecast, rather than just comparing with some like so-called ground truth labels. And the traditional temporal graph reasoning methods, they are based on heuristics, they try to learn from the history, and the neural models do not give any hint about why they make such predictions. And that's why we think that LLM can naturally give us human readable explanations by speaking from the output of the language model. And then we start to wonder, are the pre-trained LLMs strong enough? Unfortunately, they are not. LLMs are not as good as traditional graph learners when they are not fine-tuned. But graph learners are tuned on some in-domain training data. Andy has also introduced some of our collaboration before, our last work. He tried to use the in-context learning to how to say incentivize the ability of graph reasoning from language models, but we still found that the performance are not that SOTA, cannot be beating all of the SOTA trained models from traditional perspective. And it is shown that LLM's reasoning power can be enhanced by reinforcement learning in recent works in a lot of domains, for example, math, for example, physics, for example, coding. And the language model will undergo a try and error learning through reinforcement learning. This is a very important point. And the experiences associated with higher rewards are reinforced during training, and it can enable the model to self-explore and improve its reasoning. And that is the motivation why we want to use reinforcement learning to do that and try to let LM to self-explore these reasoning strategies for link forecasting. And there is another summary of what we have done in this work. First, we propose a framework. It's called RealTG. It enables LM to perform explainable and effective link forecasting on the real-world temporal graphs. And we introduce a new evaluation protocol for link forecasting with LLMs that assesses not only the prediction accuracy, but also reasoning quality and impact of hallucinations. And our fine-tuned model based on the QN3 4 billion, we call it real TG 4 billion, outperforms much larger frontier language models on both seen and unseen graphs. So here, unseen graphs are like the graphs like some inductive learning or like what we expect a foundation model to do. And in addition, our fine-tuned model can produce high-quality explanations as confirmed by both LM judge and human evaluation. Then let's see how we formulate our task. So the definition one, I think everyone in this reading group has to be very familiar with. So I'm not going to go into details here. But the second one is that we try to formulate the temporal graph link forecasting from a binary classification question to open-ended question answering generation. So in this way, we don't need to check whether a link exists or not. We instead check like given a query, a source node, and a timestamp, what is the missing destination node? It is just like how a temporal knowledge graph link prediction are doing rather than the general dynamic graph. And why we do that, if we take a look at both definitions, we can see that the traditional methods, they do binary classification on a positive link, normally when they do the evaluation, and plus one or several negative links based on the sample destination node. It means that each link consumes one forward pass in the neural model, and each forward pass will require some time and computational budget, and it will require number of nodes of times or forward passes to test all negative links for the positive link. And if we try to formulate into a QA generation task, we only need to do a single forward pass to get all predicted nodes, and it will consider all nodes in one pass. It means that we can cut the computational budget actually to a very great extent in the evaluation or like in real world application. And then let me give you another introduction about our framework. So here is the overview of our framework. It looks quite easy. And to predict, let's say this QA-based query, the source node UQ and the prediction timestamp TQ and its history, we will first employ one temporal context graph selection. It is just like sampling the history, but based on some strategies. So we construct a context graph called GC that is most relevant to the query based on the history. And we try to verbalize all the links in this context graph and combine them with natural language question derived from the query into a prompt template. And we will feed this prompt into a language model and extract the prediction answer. And in the end, we will try to compute a link forecasting reward for each prediction. And how we define our strategy in sampling the history, we do it in this way. So we first will input the graph context as text into the LM to ensure the explainability, since we required output reasoning trace in text to explicitly justify their predictions in natural language. And we aim to include as much relevant graph information as possible while we do not want to exclude we want to exclude the redundant details that do not contribute to prediction. And given a query, we construct a context graph centered around a temporal node. And this temporal node is constructed from the query. Yeah, and we start from this query temporal node and we perform a so-called like alpha temporal random walk inspired by a very nice work. It actually proposed like the personal page rank in the temporal graph. I just did a modification on it. And at each step, the walk terminates at the current temporal node. We call it ET. It's also a temporal node with a probability of alpha. And with 1 minus alpha probability, it will continue to explore to traverse the graph in the historical temporal neighborhood. And if the walk continues, the transition probability from one node to another node is given by some kind of softmax function. And in this softmax function, there is a hyperparameter called beta. And this beta is a decay factor. Sorry, there's a typo here. The decay factor indicates our intuition is that we want to assign the higher transition probability to the temporal nodes that are closer in time to the current node we are standing on. And then after we do this alpha random walk, we compute the probability of the walk starting from the query node and terminating at one of its k-hop historical neighbors. Here, how many k-hop historical neighbors will be involved depends on how long is the work, and also depends on alpha and beta. And we will rank all visited temporal nodes by their termination probabilities and select the top ranked nodes. We use this NQ to represent the set of nodes, and we think this set of nodes are the most relevant for answering this query. And we try to retrieve all of the links in the ground truth graph that we have seen in the history that involve nodes in NQ and collect them into a context graph. And here I give you a very simple example of that. And we see that the query node is UQTQ, and it has one hop neighbor E1T1 and E2T2, and it has a two hop neighbor E3T3. We see that it starts from UQTQ and has some probability going to E1T1 and E2T2. And since you might have seen that actually T3 is greater than T2, which means that E2T2 is also a historical neighbor of E3T3. So the walk will also go from E3T3 back in the direction of time to E2T2. And that's why E2T2 has two components as the sum of its final score as the termination probability. And if we try to only select one node into our top ranked node, we will finally get E2T2. And this context graph is based on all of the links involving E2T2.
Um, just a quick
Yeah.
question and give a little bit more intuition about this. Um,
Mhm.
so if you have a node that have a lot of past neighbors very recently, one hop neighbors, let's say your budget
Mhm.
is 30, this node has 50 recent neighbors that are all one hop. Does it mean
Mhm.
that it will basically never sample any two hop neighbors because of the decay factor, or a small
No.
fraction will be sampled?
No, this algorithm only dump every irrelevant node after everything has been found. So when you try to assign the scores, you assign scores to everything in the graph, and then it cuts in the end. So it doesn't cut after every step. It cuts after all steps are done. Yeah,
Hmm. So
yeah,
which means that the top K you retain will have some first hop, some second hop, some three hop.
exactly. Yes, exactly.
Okay.
Yes. Yeah.
Okay. Thanks.
And yeah, and then after we have this graph, it might be running for some time, and we will have this context graph, right? And we also have the query. We can construct a prompt template, construct a prompt. Sorry, the template is here, like how I label as green, which is the context graph, and what is the query. So here is the purple, which is filling this information here. But here I just show you the prompt template. And I want everyone to pay attention to the red boxes I have shown. So basically, in the language models, if we're dealing with the reasoning models, most models, they will just try to put the reasoning part between these think tags, and the answer part will be in the answer tags. So we just reuse this kind of intuition and try to constrain our model to put all of the reasoning in this thinking tags, and we try to output them within the answer tag. It helps us to easily retrieve the thinking as well as the answers in the end. And also for the last red box, you can see that I said if the answer contains multiple query destination nodes, please provide all of them because we only do one time of QA rather than checking all of the links associated with one query. So in this way, we try to like predict a lot of links at the same time, actually. And after that, let's see how we fine-tune the LM with reinforcement learning. We assume the LM output as this big O, and we let the content between the answers be this, it's just a symbol, A answer. And we want to parse it into a set of predicted nodes, and we want to compute a link forecasting reward. This link forecasting reward is just based on F1 score. It's very easy. Why we need to do that, we just need to recall that we, at this time, try to predict all of the answers at the same time. So we might probably have more than one answer for each query. So we will have this definitely like naturally precision and recall problem here. So we try to use this F1 score to constrain it. And this reward depends solely on the model outputs. It does not assign any reward, or like let's say it is not affected by any reasoning intermediate steps, and it will encourage LLMs to discover the transferable reasoning patterns across graphs without constraining their reasoning traces. And then we just use the most popular one, the GRPO. It does not need a reward model. We don't need to load several language models at the same time. Super quick, super easy. I will not go into details in this equation. You can refer to the reference below. And for the next problem is that, okay, we still need to record that we want to do something like a foundation model. So how can we apply our model to other graphs without retraining? We try to include as diverse information as possible during our collection of training data. So we collect 1,000 link forecasting queries from 4 TGB datasets. They are more or less evenly taken from 4 datasets. TGBL Wiki and TGBL subreddit, a lot of the answers to these queries are based on the one-hop neighbor. And for the TGBL coin and TGBL flight, they are much, much larger. And a lot of answers reside in father history and in multi-hop neighbors. And that's why I chose these splits. Of course, you can put more. I chose this amount of 1,000 because in a lot of works about IL fine-tuning on LLMs, 1,000 training data is enough for them to gain a lot of performance gain. So I do it, and each query may have more than one ground truth answer, so the real evolved links are larger in the number. It was around like 2,000 links in total. And we skip the queries where the context graph selection, temporal context graph does not contain all the ground truth answers, because in this way we don't have any positive reward, and it will not let the model learn anything. And next, we also skipped where the temporal context graph exceeds 600 links. For each link, we have source node, destination node, and timestamp. It consumes several tokens. And for the 600 links, it's just a gut feeling that, okay, I see the input context graph is super huge. I don't want them to be so huge. So I just strip them away because I think the context consuming most of the context window, and they will leave the limited space for reasoning. As I have mentioned, we have fine-tuned our model with the real TG and based on the Korean 3 4 billion, and we name it as real TG 4 billion. And then let's see how we propose a new evaluation protocol for TG link forecasting. So just everyone will be doing prediction label evaluation in previous work. And for LLM, we should also do that. So first, we would just follow Andy's previous work to evaluate with mean reciprocal rank. And how to compute the rank for a node in the QA style formulation is that we assign score 0 to all nodes and then assign score 1 to nodes included in the prediction set. Remember, from the LLM's output, we have a past set of answers. This is the prediction set. And we will compute the mean of the optimistic and the pessimistic ranks, just following previous works. And we start to think that, okay, there might be some problem because LM will hallucinate and they are prone to overgenerate a lot of answers because we try to look at the reasoning trace and the answers returned by the LM. We found that the bigger models, the larger models, for example, Llama 3, 70 billion, it will generate more average number of answers compared with some smaller models like QN3, 4 billion and 8 billion. This is very interesting. Um, and during the reasoning, or let's say during the evaluation, the MRR only cares about the ground truth nodes. They don't care about like whether you have like some incorrect nodes. So we try to penalize this kind of like overgeneration problem. We call it overgeneration problem. So maybe these nodes are correct. but we don't know because it does not reside in this, let's say, the ground truth set. But it doesn't mean that the predicted nodes from Llama 370 billion, the excessively predicted nodes, it doesn't mean that they are incorrect. If the language model can give you the reasonable explanation or justification, right? So we try to first propose this penalized MRR to capture the overgeneration, um, because now let's say we switch to the focus on the prediction accuracy. And first, we don't care about the reasoning quality. We don't care about anything. We just want to like suppress this overgenerate problem. So we use this penalized MRR, means that we might have some nodes that are not in the ground truth, but are also returned by the prediction. We want to capture the effect of it. So we assign a slightly larger score than 1. It ensures that incorrectly predicted nodes are ranked above the correctly predicted nodes. It will um, it will decrease the MRR, but by comparing the difference between the penalized MRR and the real MRR, we can capture how, let's say, how strong is this overgeneration problem. So then after that, we have solved the problem of the prediction. Then let's switch back to the reasoning problem, the reasoning quality that I have mentioned before. So how we do the reasoning trace evaluation, which has never been done before, is that we try to use an LLM as a judge system. And why we think reasoning evaluation is crucial is because a trustworthy forecaster, as I mentioned, should not only produce accurate predictions, but also provide reasonable justifications. And the predictions outside this ground truth are not always undesirable if they are supported by strong reasoning, right? We have tried to like forget about it in the penalized MR, but now we have to focus on it in this reasoning trace evaluation. And in the real world forecasting, the ground truth labels are unavailable before these events actually occur, unlike in the experimental setups. So we use this LM as a judge to do that because it's quick, it's effective. We don't have to look at it all the time. And it has been demonstrated in a lot of previous works that it works. And to save the budget, we use the GPT 4.1 mini. And to dig into the details, we try to evaluate the reasoning trace from three perspectives. First is the faithfulness. It is just to check whether the LLM's reasoning is supported by the input context graph, and it will help us to reflect the factual hallucination. And we try to split a reasoning trace into a series of atomic claims, each describing some aspect of the graph context, and then determine the proportion of the claims that are faithful to GC. So we will have a faithfulness score, which is ranging from 0 to 1. And then we try to capture the effect of the logical consistency. We just try to check whether the reasoning follows a coherent and valid chain. It helps us to capture this logical inconsistency hallucination. And we disregard the faithfulness and focuses solely on whether the LLM's reasoning proceeds in a logically sound manner without self-contradiction, and it will be ranging from 0 to 1. It will be ranging from 0, 1, and 2, and then after that we will normalize it into 0 to 1 in the end. And the last part is the answer explanation alignment. Now we have a lot of prediction answer. We also have some reasoning trace. We want to see that whether the predicted answers are justified by its own reasoning. So we call it justification hallucination. And a predicted node is considered justified if the reasoning trace contains explicitly supporting claims for it, and these claims are actually faithful. If these claims are not faithful, even if you are supporting this answer, it is still wrong. And here is the whole prompt. Um, I was just splitting them into three parts in previous slides. And next, after we have these, like, let's say the foundational building blocks done, we do the experiments. So the data set of evaluation is that we select the last 1,000 queries from each of the 6 TGV datasets in the reverse chronological order to to show that actually we want to maintain more history, as much history as possible. Because if we try to randomly sample or we sample from the start of this one of this data set, the historical abundance is very low. So, and then for each query, we then extract the context graph using our algorithm, and we filter out the queries following the same principles adopted in query skipping when we are collecting the training data. And we in total got 4,246 evaluation data. Just remember that when we are sampling, we actually don't include any bias. We don't we just try to do it. This is all of the policies we have followed in the sampling. I don't think it will include any bias, like it is in favor of our model or it is not in favor of different other methods. So I think the evaluation is fair. And these 6 TGB datasets, we reuse the 4 datasets we have seen in the training, wiki, subreddit, coin, and flight. We also include 2 unseen graphs, UCI and NROM. And for the baselines, we try to compare with the non-reasoning models, Gemma 3, 4 billion and 12 billion, and Llama 3.3, 70 billion. And for the reasoning models, we try to compare with Qwen 3, 0.6 billion, 4 billion, and 8 billion, and also the GPT-5 mini. So here is the result of the comparison across language models about the prediction accuracy. So within the same model family, the larger model size generally leads to a better performance. This is our observation. And we also see that the larger LMs, as I have mentioned, tend to predict more nodes as answers. It is shown by larger difference between MRR and PMRR, right? We think it is because their strong capacity allows them to consider more candidate predictions, although this behavior is not always beneficial, right? Because we have the ground truth label in our experimental setup. We just found that you are generating too much. And then the real TG 4 billion will outperform all baseline, including GPT-5 mini and Llama 3, across nearly all datasets on both seen and unseen graphs. We also observed that our fine-tuned model achieved substantial gains over its base model, confirming the effectiveness of our training framework.
Just
And
a quick
then,
question.
yeah, please. Mhm.
Why do you think the large LLMs generate more answers?
I think it's not why do I think like that. I think it's just an observation.
Yeah,
Um,
but like, do some guesses on the reasoning is what I'm saying.
I think larger models, what I observe is that smaller models, sometimes it will be stuck in the loop when they're trying to reason and they cannot get out this reasoning loop. And but larger models, they try to observe from a more general, like bird view, like a higher perspective. So um, I, even if we have fine-tuned our model and it shows very good results, it also contains a lot of nonsense in its reasoning. Its reasoning is longer than Llama 3.3 and GPT-5 mini. I cannot see all of the reasoning trace of GPT-5 mini because it is black boxed. Um, but I observe from Llama, I feel that Llama tries to answer it in a more human readable way, not like trying to self-correct so much. It's also because Llama 3 is not a reasoning model, but it is worth studying actually. I would say that maybe Llama with a bigger size, or let's say not Llama, maybe other models with a bigger size, they try to naturally use more strategies than the smaller models
Hmm.
because they have more parameters. But there is no, let's say, it's not causal links like between these factors. It is just my observation. Yes.
So, I guess what I'm trying to say, and also this very interesting discussion, but from my experience working on TG Talker, I also see that the larger models they have basically new explanation categories that
Hmm.
smaller models don't have. So kind of
Yes.
similar to what you are saying. So I
Yeah.
think it's the chain of thought reasoning process is different. So because your RL is still based on their own reasoning trace, if the model is small and they just come up with, let's say, 6 different explanation or ways to do explanation, then that's only 6 you can learn, right? But maybe larger models they can do more diverse reasoning categories. So then maybe it leads to more answers in this way. But I'm not sure. I think it's like very interesting to see where does it plateau? Like at what point does more parameter don't give you more explanation categories? Like, or do they
Yeah.
converge at some point?
Yeah, yeah. I would say like your intuition is completely correct, and I think it is a problem of correlation. It cannot be explained because we still don't know why. But my personal observation is also that the larger models can like having can think out of the scope, you know.
Hmm.
It can
Hmm.
help you to, it can give you more ideas sometimes because maybe I think from my understanding it's because more parameters can help us to preserve more knowledge in the stored in this language model. And when you try to trigger it from some hint, it can help you to better trigger it. Um, this might be the explanation or the reason behind that, but I'm not sure because I have never seen anyone successfully persuade everyone that their explanation is correct to answer this question. Yes.
Right. That could be interesting, but we're going off a tangent. But let's say we have a bunch of these models that we use for explanation, and we let them actually argue among themselves to
Hmm.
agree upon a single explanation. And I'm curious
Hmm.
what that would be. Like you just let them talk to themselves, like a
Hmm.
multi-agent system, and they try to consent on this should be the ground truth explanation for this. I mean, there's no ground truth, but let's see what the LLMs can come up with.
Hmm.
Um,
Hmm. Hmm.
but yeah,
Yeah, it might be interesting. Yeah.
but yeah, yeah.
Yeah.
Please continue.
Yeah. And then let's see our evaluation result about the reasoning quality. Here, just to speak ahead, I have excluded GPT-5 mini because we were using GPT 4.1 mini, and there is a showing proof that they will introduce family bias, which means that we use GPT model to do the LM as a judge to judge the GPT, another GPT model. It will assign a higher score because they are trained like somehow. Um, like similar way, right? And the findings of this reasoning quality is that within the same model family, we still observe that larger models will exhibit greater robustness to the hallucination, and it shows a higher reasoning quality. We think that there is a correlation between the accuracy and the reasoning quality, and it's also an observation, and we cannot prove that. It's just an empirical finding. And also, the real TG4 billion helps us to significantly outperform its base model in reasoning quality. And it can demonstrate that our framework can help LLM to discover more meaningful reasoning patterns. And despite these gains, we still observe that our fine-tuned model trail larger models in logical consistency and answer explanation alignment. We think it is likely due to their stronger reasoning robustness by these larger models. And this is just what we were talking about on the previous slide. So we think, even if we haven't done the experiment because it is too costly, we still think applying our framework to the larger base model will be a promising direction in the future. And it has also been proved by RL fine-tuning work in other domains. And also to supplement, yeah, and also for to persuade the reviewers, if we submit to somewhere, we try to compare it with the traditional methods. We consider the recent traditional TG-link forecasting methods, several temporal GNNs, TGN, classic work, digiformer, another classic work, and the TNCN, which is a new work, and also the SOTA right now. And we also try to compare with a heuristic-based method, EdgeBank, which is also super popular and easy to implement. And we train the TGNN separately on the original training set of each involved data set and evaluate on the same evaluation data. And here I need to specify that what I mean by original training set is all of like the whole training set of the TGB in Wiki, subreddit, Coin, Flight, UCI, and Enron, rather than our 1,000 data instances. And to avoid excessive cost, we control the budget for evaluation with a timeout constraint of 24 hours because we need to use H100 GPUs. And our fine-tuned model can outperform strong traditional methods as shown in this table here. and it can also provide the explicit reasoning to justify its predictions where they are missing for the traditional methods. And the LM-based QA style link forecasting can help us to enable the low-cost prediction in real-world applications because we found that, for example, for TGN, digiformer, especially digiformer, I think it is super, super slow because it has a very, very huge transformer and it needs to be run for a number of node times for each link, while we only need to run one forward pass. And our model can eliminate the need to train a model from scratch for new TGs. For example, let's see this UCI and Enron here. Our result is achieved by zero shot, but they have trained on the whole training set, but they still get a very low result compared with our model. And also, we have studied the influence of the base model size on our framework. We try to train a separate model, which is based on a very tiny reasoning model, the smallest reasoning model, QN3 0.6 billion. And we evaluate its traces with our LM judge and compare them against the 4 billion one, including the base model and the fine-tuned one. And the result is shown in this table. And the findings is that training from a smaller base model result in significantly worse reasoning quality. And this is actually expectable, right? We observe a notebook case of reward hacking even in the 0.6 billion model. To be specific, it is that in many cases, we found that the model is claiming that, okay, your to be predicted link has already been seen in the provided graph context, which is always impossible in the forecasting task because we in the context graph we only have the historical information where any information at timestamp TQ has never been seen. So we think that weaker models cannot effectively self-explore reasonable reasoning strategies. Recall that I have mentioned one sentence in previous slides is that the reinforcement learning models, they need to do the trial and errors. If the trials are not reasonable, if your model is too weak to give you the great trial, you can never get a good policy in the end. So we confirmed that using a larger base model will enable much stronger fine-tuned performance. And after this fine-tuning, 0.6 billion can achieve reasoning quality comparable to QN3 4 billion. Well, even if it has some reward hacking, even if its quality is trailing compared with the larger models, it still underscored the effectiveness of our training framework. And in the end, we have done two human evaluation. The first evaluation is that we are evaluating on the quality of the reasoning traces directly. And we try to recruit 5 annotators to evaluate the quality of traces output by the 4 billion trained model on a random sample of 50 data examples. And we average their annotations. We get the high scores of this almost like close to 1 or let's say close to 0.9 answer for all of three like reasoning trace metrics, and the maximum score is 1, and it closely aligned with the judge's score. So we think that it helps us to validate the LM as a judge system, our prompt design, and everything. And it also demonstrates the substantial reasoning capability gained through the fine-tuning. And also the second human evaluation is that we use humans on the same 50 samples and try to collect both the responses generated by language model and the corresponding judgment from the system and ask us humans to try to evaluate how do you think the quality of this judgment? How do you think of these comments generated by the judge about the quality of the reasoning trace output by our fine-tuned model? And for each of the three criteria, annotators assign a score from 0, 1, 2, which is same as before, and with higher values indicating better judging quality. And the resulting average scores are 1.71 for faithfulness, which is also close to 2, 1.88, and 1.71 for the other two criteria. And we think that it already helps us to capture some excellent judgment quality. Yeah, that's it. Yeah. And I have, after doing this work, or in the process of doing this work, I have thought about several problems. First, for the summary is that what we have achieved is that we have a new paradigm for training link forecasting models with LLM, and we also prove that the IO fine-tuning works well in enhancing LLMs in TG reasoning. Um, by talking with my colleagues, and we still think that we have a long way to go. The core problems we're studying in the near future is that if we try to use LLM for graph reasoning, first is that can we efficiently compress the graphs to fit into the limited context window? Um, if you pay attention to the previous slide, you know that I have skipped um, every cases where there exceeds 600 historical links. It is actually very bad for graph in the real world because in the real world we have so many histories and we don't always want to skip all of them and we want to input them into the context. But LLM has limited context window, so how can we solve that? It is also a very heated topic in the pure natural language text works for the LLM. People use memory, people use a memory bank or agent to retrieve. People use RAG, something like that. Also, another question is that how can we effectively reconstruct the compressed graphical information during reasoning? Assume that we now have a super compressor to compress the graph, uh, very huge graph that cannot be fit into the context window, and we compress it into some low dimensional vector, and we try to fine tune with the soft prompt as in previous tries of previous works. How can we reconstruct it? Why we need to reconstruct it? Because if the language model only sees this latent embedding, it does not help you to judge whether the output is faithful to your input from human observation first. Second is that maybe it is even harder for them to give you the reasonable explanation for your forecast. This is also centered around the core problem in forecasting is that we need to trust a forecasting system when we know that it is giving you something sensible rather than some nonsense or only giving you a label. If it only gives you a label, we never know how can we trust it, right? And the third problem is that how can we make the LLMs better at other downstream tasks in TG reasoning, which generalize a little bit more steps to the direction of TG foundation model. And even if we can make them good at more downstream tasks, does it really mean that we achieve a TG foundation model? I don't think so. Even if we train the model with RL, we design several reward functions for node, affinity prediction, or like graph predictions, three levels like link level, node level, or graph level. It doesn't mean that we are achieving 2G foundation model because in text foundation model, we try to unify everything in text generation. How can we find a task that can unify every graphical task, any downstream task in graphs? This is a very important problem when we try to achieve a graph foundation model. Yeah, that's it, Andy.
Great. Yeah, thanks for the great presentation. And yeah, thanks for presenting the material very nicely. If you have any questions from the audience, feel free to type in the chat. Um, and I guess follow up a question on what you just talked about on future work.
Mhm.
To you, what does it mean to be a TG foundation model?
For me, not only TG foundation model or graph foundation model, all of them, let's say, I think it's a function, whatever it is. This function can be neural symbolic, can be neuron or pure symbolic. This function takes in the graphical structure, encoded in any way, and then outputs something that um, that tries to answer your question about your graph, or that tries to output something that can help you to understand what you want from this graph. This is what I call from foundation model. I don't think now anyone has achieved that, especially in graph. So I have read recently there's a very popular paper in graph called G1, right? From Peking University or something. Yes, they tried to fine-tune with IL with a lot of like fundamental graphical reasoning tasks. I don't think it's a foundation model. I think it just tells LLM to memorize something from the textbook. It is not applicable, as I think, in the real world cases where you really want to get something from it. It's
Hmm.
not like language model. Yeah.
Hmm. Um, and I think on this work as well. So I think due to limitation of compute resources as well, so we can only fine tune up to 4 billion size model, right? But
Yeah.
if we have compute to fine tune a 70 billion or even larger LM on this, I think it could also give a lot more interesting like explanation categories and traces. And
Yeah.
yeah, I think it's not
Yeah.
clear what to expect the model will do in that case. Um,
Yeah, I feel that the technology is there. We can do something as long as we spend some time and energy in figuring out what is the basic task. Like, what is the task that is as important as next token prediction in language model? Let's say
mhm,
in the graph, what is a task as important as it? If we can figure out this task, let's say we can get it. Yeah,
mhm, mhm. Well, I think like link prediction in temporal graph is one of the most basic tasks because it's, you are taking step by step going to into the future,
yeah,
right? If you're talking about a subgraph prediction task, you could be predicting a subgraph, the sequence of links that happens in the next period of time. And
yeah,
then for node tasks, it's slightly different because the node labels are not something that directly derive from the graph structure. So it could be
yeah,
some attributes or something.
yeah,
So I would say with graph, it's actually not very clear even how do you have a foundation model for all tasks,
yeah,
because you cannot have a single representation that represents all
yeah,
information very well. If you have a graph embedding, it loses node specific information and vice versa. Um,
yeah,
so I think it's a very interesting thing to think about and can also tailor it more towards like actual useful applications, like, you know,
yeah,
uh, getting the good reasoning traces, understanding it, and maybe using it to design better graph model. I mean, that's something we discussed during the
yeah,
project. Um,
yeah,
so yeah, so I think definitely a very promising direction to continue on.
yeah.
Yeah. Okay.
Um, can I
Yeah.
ask an understanding question?
Yeah.
I'm also working on link prediction, but I don't use any language model. I probably use language model to encode the text as a text encoder, but in general, I don't use prompt and this technology to do link prediction. My question is there any theoretical principled way that we can theoretically interpret what is the reason that we have seen the improvement in language model? So maybe give an intuitive example. In graph representation learning, is very famous theoretical frameworks like Westphal-Lehman test, and you can theoretically prove that GNA is same expressiveness first dimensional Westman-Feller test. But if you have node embeddings, it's maybe you maybe should better to use second dimensional Westman-Feller test. And in link prediction, it's already showed that graph neural network is not really good at it because it cannot really distinguish automorphic nodes. So my question is there any such principal theory exists when you are doing your project or what you're exploring? And how can you theoretical reason that the improvement in your model is coming from the better representation power, but not just the more computational cost, the better parameter sufficiency, and so on?
Mm, I think no. Um, I think language model, these people, they are more practical. I'm not saying like doing graph representation is not practical. Like language models, these people, like everyone is hyped. Ah, OpenAI is releasing something. We like actually they try to solve the problems from a more technical side rather than the theoretical side. Weissman, sorry, I don't remember that name. I know what you're talking about. The thing is that um, I have a slightly different opinion on one of the stuff you have mentioned is that I don't think um, our model is getting better because it has more parameters than GNN. I think it is just the perspective of how you reason a graph to do link prediction. Personally, when I look at the reasoning trace of the language model, I see that it always have several patterns that are very popular in these real-world temporal graphs. For example, the repeated edges. For example, um, the periodicity. For example, like the increasement of the frequency that something happens. Um, it tries to predict the links in a different way as a GNN. The GNN tries to learn embedding and get the similarity. Uh, I don't think language model is computing any embedding of the node or edges during this reasoning. It just tries to find a way that how humans are trying to predict the future in the graph. Why? Because it is trained on the vast language corpus based on the web of the human language. So um, I don't think it is easy to find a theory behind that. Um, that's why a lot of people they try to theoretical support rather than just trying to convince people that scaling is the winner. So I can't answer your question, but I'm just sharing you my opinion. Yeah,
Okay, thanks very much.
yeah.
Um, and I think for the expressiveness, I think expressiveness in temporal graph is a very interesting topic. But I think we still don't have a single framework of expressiveness on temporal graph that are really giving us in like practical insights into how we should design models. So people do models in different ways. You have one-hop neighbors on the IG former, which works
Hmm.
pretty well
Hmm.
sometimes, and you have like message passing ones. You have graph mixer, which is just MLPs. So people do all kinds of stuff on temporal graph. It's not clear what they are actually learning or why they work.
Yeah,
They are usually motivated by some sort of law, like triangle closure or, like one hop
yeah,
neighborhood, you want to find like recent neighbors or something like that. But
yeah.
it's not very clear. Um, and I also believe, similar to what Zifeng said, is that LLMs do link prediction in a different way than GNNs. And I think the two sets might there should be some there are definitely common things between them, but I believe they are also complementary. So there will be
Hmm.
links where TGNNs can predict and LLMs cannot, and vice versa. Um, so I think yeah, so I think it's a very interesting problem to think about. And ideally, in the future, you can like advancements from both like TGNN and LLM can kind of help each other um, find weaknesses in their reasoning or architecture design. But yeah.
Yeah, but I still think the theoretical support is very important. Unfortunately, I'm not a theory guy, so I cannot comment a lot on this. But I'm happy to work with some people who really can tell me the theory. Like in the slides that Oxford students talking with me is a very theoretical guy, and he has a lot of theory proof in all of his papers. So I just consult him whether I'm saying something correct when I'm saying something incorrect. And yeah, I think what Andy says also inspires me a little bit. Like I think we don't have to make a choice, right? We can combine them both. Like why not? A lot of work now are also combining GNN with language models. Language model is just a verbalization of the reasoning and of what has been compressed by the GNN or what has been learned from GNN. If we can also find some theoretical way to prove that, okay, language model is saying everything that has been captured by GNN. I think it is also something that is worth studying. Yeah.
Yeah, I think just give the short comments to explore the research methodology of it. Actually, in graph neural network, we also be tired of this Weissman filter test because it originally is tried to explore whether GCN is able to tell the differences between two orthomorphic graphs. That is a very famous limitation of GCN. People keep studying it because we know that theoretically it's difficult. If you can identify very difficult case for language model to the link prediction that all the language model fails, you can also try, if you have very strong empirical study that in a specific scenario that all language model related method will fails, you should really start principle it and make like the classic example and try to build a theory based on that. That is how
Mhm.
the graph theory has been built for GM, the Western filter test. Yeah, that is what I think how what you call theory guy is doing the theoretical research in graph neural network. And if you are also interested to explore the theoretical framework for language model on graph reasoning, so maybe you also worthwhile to try to do the research in this style.
Yeah, 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 yeah.
Yeah, for sure. Definitely very interesting. I think we do know that from the experiments that the LLMs are not good at inductive tasks. If a link is if the data set is very inductive, very few repeated edges, I think it still have difficulties, right, Zifeng? I think we saw
Yeah,
something
yeah, yeah,
like that
definitely.
before.
This
So,
is this is, I even don't think GNN can do that. This is something also very tricky. Like in real world data sets, we have a lot of like abrupt signals. Like it just pops out without any
so
reason.
last week's talk, actually, but you can watch when it come out. But last week's talk was actually having a new architecture to in TGNN to work specifically on kind of this inductive setup. But
Mhm.
it's more for like bipartite graphs.
And the thing is that in this work, we try to exclude every textual attribute, everything. We just preserve this topological structure because we just want to focus on this part. Like, how can we reason over the graph itself rather
Yeah.
than using some textual attributes? Like, of course, if I have textual attributes of, or let's say the node attributes, like I can say everything. Like, I can do the inductive task very easily. But only with the graph, it is really hard, I think. Yeah.
Hmm.
Yeah.
Yeah. Yeah. Okay. Yeah, thanks for the discussion. Are there any other questions? Otherwise, we can wrap up here. And yeah, thanks for coming to the talk, everyone. And yeah, let's thank Zifan for the great talk again.
Thank you. Yeah.
Thank you.
Yeah.
Bye.
Bye.